Okay, hi Science 30. I'm going to finish off this section of the unit with transformers, up to the end of transformers here. So I believe this is slide 57 in your notes. Slide 56. Then you'll have all the material you'll need to do the first electromagnetism quiz. Just finishing up with circuits. Page 384 has some review questions. Specifically, kind of 7 to 12. Those are good practice questions if you need those. We're going to talk about transmitting electrical energy. So this is section 1.5 in your text, page 385. We're going to look at power and energy and things like watts. Okay. So just to end up the series in parallel circuit conversation, so you can see that this is a household grid. So you can see that some of the grid is attached in parallel and some of it is in series. So you have a combination of series and parallel circuitry in your house. Switches turn bulbs on and off, or power sources on and off. Okay, so looking at transmitting electricity, we look at the movement of electricity in a unit of power. So how many units of energy per second we can move. So power is a quantity used to describe the rate of doing work or transforming energy into something useful. So energy used over a given duration of time is what power is. We don't always refer to electrical systems with power, right? For example, if you do any road cycling and you have any calculations, you can measure the power that you're producing while cycling in watts, and so that's a way for you to look at fitness transitions and things like that, and different types of workouts. Anyway, the goal of electrical devices is to produce the required quantity of useful energy while consuming the minimal quantity of electrical energy. Right, so that's what we want to do. We want to make the greatest amount of mechanical energy for the least amount of electrical input. So power is measured in watts. It's in joules per second. Work is kind of energy with a point. So it's energy that's being input into a system to do something. Work and energy are both measured in joules, and we're measuring this in power equals watts over time. Okay, so page 386 has an example problem looking at power. Here's a sample problem here. This is page 387. Page 39, a family shopping for a new refrigerator has narrowed its search down to two possibilities. The first model is rated at 700 watts, and the second is rated at 500 watts. Determine the quantity of electrical energy used by each model in a day. Assume that each model runs for 6 hours every day. Okay, so the amount of energy used in a day. So energy equals power over time. So this is in your... Okay, so this is in your formula book. So you need to do two things here. All right, we have to solve for power. We know that power equals watts over time. And then we need to solve for energy in joules. All right, so if I have a 700 watt appliance and I have a 500 watt appliance and they run for 6 hours each day, go to your conversion factors to solve for this. So if I look at how many time, right? So 1 hour equals 3,600 seconds. So I know that 6 hours times 3,600 seconds per 1 hour. I can cancel my hours out. I know how many seconds that's going to be. 6 times 3,600. Oops. Okay, so I know that that's 21,600 seconds. So that's my time. Let's solve for power. So the power for the 700 watt appliance, so the 700 watt refrigerator, is this. Okay. Sorry. That's my power. Right? I don't need to solve for power. I've been given power. I can use energy. Energy equals P times T. I could derive power if I needed to. Anyway, I was a step ahead of myself here. So energy equals power times time. I have 700 times 21,600 seconds. That's going to give me an answer in joules. So I'm going to have 15 million 120,000 joules for that. So that's 700 watts. E equals P times T equals 500 times 21,600 seconds. So the energy here is 10,800,000 joules. Okay, so that's the energy difference between the two of them. Right, the 500 watt model, will use less joules of energy. Therefore, you'll require, less power from a power plant. So if that's coming from like a coal-fired power plant or something, less chemical energy needs to be burned to deal with that. Okay, so that's E equals P times T. And power equals watts over time. So we're going to combine these two in another question in a second here. This is something that you can look at as well. So we actually determine our utilities bills in kilowatt hours. So we know that energy equals power times time. So 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules. Time is measured in hours. So we can calculate our power bills from these equations. So this is in 2014. Power's about the same right now, a little bit cheaper, just because we're not using it as much due to COVID. Anyway. Okay, so page 391, example problem 1.18. It walks you through a few examples of how to calculate how much an appliance would cost based on these equations. So I'm going to give you an example. Okay, so if we look at number 46, number 46 on page 392 says, after listing all the devices in her home that use standby power, Michaela determines that the total standby power consumed by the appliances in her household is 87 watts. Okay, so 46, page 392, power is 87 watts. Question is asking, determine the total energy in kilowatt hours required to supply all the appliances in this household with standby power for 365 days. All right, so first thing we need to do is, so we're turning watts into kilowatt hours. Okay. So I have 87 watts, and I'm actually going to, so my total power, so they get this on a power bill. So 87 watts is going to be, 1 kilowatt is equivalent to 1,000 watts. So I can do that conversion. Cancel the watts out. And that is 0.087 kilowatts. Okay. So there's my power calculation. I need time as well. So time, it's asking me for, in terms of the total energy, 365 days. So I need to convert. So I have 365 days. And I need that in hours. So I know there's 24 hours in one day. So that equals 365 times 24 hours, and that's 8,760 hours. Okay. So I can use this equation. Energy equals P times T. So I have the power in kilowatts and I have the time in hours. I calculate my power bill, and that's 0.087 kilowatts multiplied by 8,760 hours. I get an answer in kilowatt hours. Okay. And that is 762.12 kilowatt hours. So there's 762.12 kilowatt hours to fuel standby power for all the appliances in this girl's house. So that's the power required just to keep appliances on, not to actually use them. So B says, if the price of electricity is 9.3 cents per kilowatt hour, determine the annual cost in dollars of the electrical energy required to supply the standby power for this household. So I've got 9.3 cents per kilowatt hour. And let's convert that to dollars. Right, so 9.3 divided by 100, right, is $0.093 per kilowatt hours. Okay, so what's the price of that going to be? So I know that I have 762.12 kilowatt hours, and that is multiplied by $0.93 per kilowatt hour, right? And that cancels out my kilowatt hours, right? Because this is dollars over kilowatt hours. And that'll give me the final price of all the standby power at that house. Okay, so standby power on an annual basis is going to be about $70.88. All right, so I can calculate a power bill using E equals P times T. and then doing a dollar conversion with these equations. Okay, some more equations with power and electrical systems. So in dealing with electrical systems, power is a function of the voltage of an object multiplied by the current. So how many electrons it can provide multiplied by how many of them flow past a certain point. So power equals current times voltage. Okay, so P equals I times V. This is in your data booklet. Okay, P equals I times V. And we know that V equals I times R as well, right? So, this is Joule's law. So if voltage isn't given, we can solve for voltage using current times resistance. Okay, so we know that voltage equals current times resistance. So P is also a function of I squared times R as a result. And you can see that equation derivation there. So we can substitute variables to get that. So there's two more power equations. You have sample problems on page 388. Example problem 1.15 and example problem 1.16. So I'm going to do page 389. Here are some problems. Okay, so let's look at number 42. Number 42 says two of the subwoofers, so this is in our car system. These subwoofers have 8 ohms. So two subwoofers in a car are connected in parallel to one of the circuits in the sound system. This circuit uses a circuit breaker to ensure that the maximum current that can be drawn from the amplifier is 5 amps. Determine the total resistance of the two speakers in this circuit. Okay. Okay. So these speakers come from example problem 1.15 and 1.16. So 42. So page 389. Number 42. I'm going to skip A where it says draw a diagram. You're just drawing a parallel circuit there. So B says determine the total resistance of the two speakers. Each speaker has a resistance of 8 ohms. So there's two speakers. Right, and they're connected in parallel. So I know that 1 over RT equals 1 over 8 plus 1 over 8. Okay. So that's 1 over RT equals 0.125 plus 0.125. So I have 1 over RT equals 0.25. So RT will equal 1 over 0.25. Okay, and then 1 divided by 0.25. So my resistance is 4 ohms. Okay, once I've solved for that, I know that there is a total current, so current equals 5 amps, resistance equals 4 ohms. C says use your answer from 42B to determine the power consumed by the two speakers if they draw the maximum current of 5 amps. So power equals I squared times R. So that's going to be 5 squared multiplied by 4 ohms. So 25 times 4 equals 100 watts. So that would be the answer to C. Okay. This says use 2 different equations to verify that the sound system is supplying 20 volts to the 2 speakers under these conditions. So D, I know that I have a total power of 100 watts, so I can use P equals I times V. So I have 100 watts, and that is 5 amps, and I can solve for voltage. And then 100 divided by 5 equals V, and that's 20 volts, so that confirms that. And then I can use V equals I times R as well. So V equals I times R. So we're verifying that it's actually using 20 volts. 5 times a resistance of 4 ohms, and that is also 20 volts. Okay, so these equations are interchangeable. So 43 and 44 also work with these power equations. This talks about where electricity comes from in Alberta. This is a little bit, this is from 2011. So you can see that we have coal, gas, hydro, other is things like wood chips and geothermal. We don't have any nuclear in Alberta. So you can see the proportion. Coal has greatly increased as gas and wind have increased. Geothermal has also increased. So we're phasing coal out, right? So we're at about less than 50% right now with coal being provided for power plants. Okay, so where we lose power on a grid, most power in electrical transmission is lost in the heat produced by electric current. So as the current moves through wires, it creates friction, and heat is lost because of entropy, right? So disorganized energy is lost. So we try to reduce that by making cables as efficient as possible with insulation and using very conductive material, trying to cool it, et cetera, et cetera. So the resistance in electric cables is reduced as much as possible by using highly conductive materials and good insulators. So power is a function of current, so you can see it's I squared, so how smooth things can flow, multiplied by how much things are resisted. So you can see the flow is is an exponent more important than the actual resistance. So if we can have a good flow of electricity, then we can reduce resistance. Okay, I'm going to pull up some more questions here. So here's some more sample problems, and you can just kind of follow along as I go through them. So this is a question here that says, what is the current through a 4.0 times 10 to the second watt electrical appliance when it is connected to a 1.2 times 10 to the second volt power line? So we have a power calculation and we have a voltage. So we can use P equals I times V to solve for that. So P equals I times V. Okay. So we're solving for current, so P over V would equal I, and you're going to end up with 3.33 amps when you do that math. So you can plug that into a calculator. This is a type of question that you are going to have on a quiz, two-step question. So the question is asking, what is the heat produced? So heat is synonymous with energy, so you need an answer in joules. Okay? So you have to know what's being asked. So what is the heat produced in a conductor in 25 seconds if there is a current of 11 amps and a resistance in the conductor of 7.2 ohms? Now we don't have, right, so we have two equations that we can use. So you have a resistance and a current, so you have P equals I squared times R. Right, you also have a time, and that's 25 seconds. Right, and we're trying to find energy. Energy equals P times T. We don't have power, so we're solving for power. So two-step equation. So again, you have 11, where am I here? I have 11 amps and 7.2 ohms, so I can solve for power. Okay, and then I can solve for heat, which is energy. So E equals P times T. Be prepared to be able to do a question like this on a quiz. Okay, here's another one, question number 6. So these are sample questions, and again, you can refer back to these throughout the video. Excuse me. You can use them as examples as you go through your quiz as well. So I have, so this is the same question, but you're going to kind of go backwards here. So you have energy, so we have 1.5 times 10 to the second joules of heat, and that is produced in a conductor in 5.5 seconds. So I can find power from that, right? E equals P times T. I have energy and time, and I can solve for and rearrange for power. So if the current through the conductor is 10 amps, what is the resistance? So once I have power and current, I can use P equals I squared times R to solve for resistance. All right, so here's what I've got, right? E equals P times T, which is 150 joules. Power is going to be E over T. Right, so I'm going to end up with 27.3 watts. I'm going to plug that into P equals I squared times R, which is right here. Okay, 10 amps. Right, P equals I squared times R, so it's going to be 27.3 times 100. And I'm going to get 0.27 ohms. Okay, so those are your power equations and the different applications that you'll have with solving for power. Okay, so the last big theme in this section of the unit is looking at transformers. So transformers are parts of a grid. They're not just DNA-based robots. So power is a device that transforms the alternating current voltage of one circuit into a different AC voltage for another circuit using separate coils. of wire around a common iron core. So, if you look at transformers in your textbook, page 397 looks at transformers. So you have an iron core and you have coils on either side. And the coils have incoming electricity. They move through the iron core and have outgoing electricity. And it's the number of coils on either side. The primary coil receives electricity. The secondary coil has electricity leaving the iron core. So it's the ratio of coils that determines how much voltage gets sent to a destination. And this is how we store energy on a grid. Okay, so components of a transformer. It has a primary coil and a secondary coil wrapped around a central iron core, as I just said. The primary coil receives the input voltage from an applied electrical force, and the secondary coil supplies the output voltage of a transformer. So this is another diagram that's kind of simplified it. So you have a primary current coming in. You have the iron core, and generally there's a magnetic field inside that iron core because the magnetic field can store the electrical current. And then you have the secondary current, which will carry the electrical load out. So this would be incoming energy from from a power station to a large transformer station, and then this would be outgoing coils to households or businesses or buildings. Okay, so transformers. You have step-up transformers and step-down transformers, and that's what our last sort of set of equations is going to be on. So step-up transformers will increase the voltage of an electrical current from one coil to another. So you'll have the voltage get larger as you have electricity coming into an iron core and then leaving the iron core through the secondary coil. Step-down transformers decrease the voltage, so you'll have less electricity leaving the iron core. And I'm going to explain how that happens. Okay, so how this works. So if a current within a primary coil is changing, a magnetic field can be induced into the iron core of this transformer, right? So this magnetic field is really dependent on this. So if you close the switch on the primary coil, you can increase the magnetic field in the iron core and induce current into the secondary coil. Okay? So I can use switches to turn these things on and off, and I can power electricity to leave the core by turning off the input of electricity at the primary coil. The current will be increased to the secondary coil by closing a switch and decreased by opening the switch. Okay? So if I close the switch, then electricity can pass through the secondary coil. So kind of like completing a circuit. All right, so those are all factors, but the